Hello, my name is Alshareef from Johns Hopkins University, and today I'll be presenting our work on integrating material properties derived from magnetic resonance elastography into subject-specific brain models. The motivation behind this work is traumatic brain injury, or TBI. TBI is a major health concern in the United States, where it's a contributing factor to about 1/3 of all injury-related deaths. But most TBIs are actually classified as mild TBI, or concussion. These are common in motor vehicle crashes, where they're the third leading cause of TBI. They're also common in sports, where there's an estimated 3.8 million sports-related concussions in the US every year. So how do we understand what's happening to the brain during a TBI or impact? Really, the gold standard has become computational or finite element models of the brain. These allow us to take what we can see or measure on the outside in terms of head kinematics, input that as loading conditions or boundary conditions in our model, and then we can output stress or strain fields that allows us to predict injury or to evaluate safety countermeasures like helmets. One of the deficiencies of these models, however, is that they're typically created from average geometries and average material properties from the literature, which can make it hard to make subject-specific or individualized predictions of risk. One of the projects we've been working on here at Hopkins, along with our collaborators, is acquiring data that can make a truly subject-specific model. This includes magnetic resonance imaging, or MRI data here on the left. That includes anatomical images, where we can get the structure and microstructure of the brain, magnetic resonance elastography images that can allow us to acquire information about the material properties of the brain, and then tagged MRI, which allows us to apply low-rate boundary conditions to a subject's head and measure the strain fields due to that rotation. These allow us to then make a subject-specific model that includes geometry from that subject, material properties calibrated from MRE, as well as then to simulate that model with the subject's own experimental data to then validate the biofidelity of that model. More information about this can be found in our recent review paper, and all of the data that I'll be presenting today can be found at the following web link. So, like I said, the goal of this project is to create and parameterize individualized subject-specific models of the brain. And the specific objectives here are, one, to assess if linear viscoelastic material properties derived from MRE can be used to generate subject-specific brain models without further calibration, and can an LVE model sufficiently capture the brain mechanics under mild head loading from tagged MRI? So to begin, why linear viscoelastic? We know there's higher order or more complex models out there for mechanics. And really one of the main reasons why is that it's computationally efficient and commercially and widely available. It has a small number of parameters, and those parameters can be derived from the low strain regime of magnetic resonance elastography at a high spatial resolution. By starting simple, it also allows for incremental investigations of more complex features of the brain, like spatial heterogeneity, anisotropy, or hyperelasticity. And lastly, but importantly here, is that LVE models have been used in brain models to develop important injury criteria. This includes the GHBMC brain model, which was used to develop the damage criteria that's used to evaluate helmets, and the Simon model, which is a model that has been used to develop the brain injury criteria, or BRIC, that's used in automotive crash safety assessments. So what does the experimental data for this data set look like here? So we have three types of images. One, all the way on the left here, is the anatomical segmentation. So this is the geometry of the brain regions of that subject. The middle is the magnetic resonance elastography, or MRE data. Here I'm just showing the storage modulus. And lastly, the tagged MRI data, which is our validation comparison. Here I'm just showing a maximum principal strain field. All of this data has been co-registered so that each point in each one of these images aligns to the same point in the other images. And here's some more information about how it was acquired and how it was processed. So what are the issues that come up when using MRE data? Well, first, MRE is collected in the frequency domain, and time domain parameters need to be calibrated for the brain simulations. And second is that it's collected in the frequency domain at a limited set of frequencies. So in this case, 30, 50, and 70 Hertz, which can lead to uncertainty in our estimation of the instantaneous and the infinite linear viscoelastic shear moduli. So how do we inform our calibration to get over these uncertainties? Here I'm showing an example of just one voxel in the brain, showing the values of storage and loss modulus at the 3 frequencies. So one of the things we can do is extend our range in the sort of y-axis by averaging across regions of the brain. For example, the cerebellum white matter or the cerebrum gray matter. To extend our range in the x-axis, one of the things we can do is use literature data to supplement the data that we currently have at those limited frequencies. And how do we do this? First, we take our subject-specific data, so this includes our anatomical regions and our MRE, and we can combine it with dynamic shear experiments from the literature where brain tissue is excised from animal or human cadaveric specimens and then tested under a large frequency range. What we can do first is take all of the literature data, so that's these background gray dots on the right figure, and interpolate them to the same frequency as our MRE data at 30, 50, 70 Hertz. And then we can scale the literature experiments. So here in blue, I'm showing the original experiment from the literature, and in black, the scaled up to the MRE data. And then we can pick a number of experiments. So in this case, I'm choosing 5. The experiments that match closer to the MRE data in both the slope and the magnitude of where they are after they've been scaled. And then I can take that data and supplement my linear viscoelastic calibration by equally weighting both the MRE data and the scaled literature data. So this extends my range in the frequency domain. So what does the model actually look like? This is an example of the model in an axial, sagittal, and coronal slice. The model has 7 brain regions, 13 in total, including the falx and tentorium, and these are segmented directly from the MRI scan of the subject. It's at a 1.5 millimeter isotropic resolution for all of the voxels or hexahedral elements inside the brain. This is solved in LS-DYNA using an explicit solver with 1 integration point, and it takes about 5 hours on 4 CPUs for 160 millisecond simulation. This is an example of that subject-specific simulation under the first loading condition I'm going to describe, which is neck rotation. So it's like you saying no or moving your head left to right. On the left here, you can see the anatomy deforming. In the middle, you can see the in-plane shear strain, so the XY component. And on the right, you can see the first principal strain over time. The second loaded condition I'll describe is a neck extension experiment. And here, the head is moving from front to back, sort of like saying yes. And again, you can see the anatomy, the shear component, and then the first principal strain. So let's go over what the strain fields look like now when we're comparing from the simulation to the experiment. And I'll emphasize here that the experiment is collected in the same individual that we modeled our geometry based off of. So first I want to focus on this first frame, which is the peak strain at 45 milliseconds. Here I'm plotting the in-plane strain components, so EXX, EYY, and EXY, as well as the first principal strain. And you can see we get a reasonable match in both the spatial distribution and the magnitude of the strain. So it's matching where the strains are happening and the sort of the magnitude of these in-plane strain components. Now, as we move later in time, we can see some differences between the simulation and the experiment. The experiment has a little bit more strain in the next time frame, but it dies away after that. The simulation, however, shows some oscillatory behavior, as you can see here, and then at 81 milliseconds. And that's reflected in all of the strain components as well as the maximum principal strain. So the takeaways here are that the model is parameterized and successfully simulated. The LVE model can match the magnitude and spatial distribution of peak strain, but it does not capture the temporal dynamics of the brain response. And to emphasize those points a little bit more, here I'm plotting the same strain components, so in this case the in-plane strains, EXX, EYY, and EXY, but I'm plotting percentile threshold percentile strains. So the 5th percentile, 25th, 75th, and 95th percentile strains over the whole brain. And in this case, you can see the solid line is the simulation, the dashed line is the experiment at specific temporal resolution. And you can see that we match that first peak strain at 45 milliseconds, and then there's some oscillatory behavior that you don't really see in the model. If we look at the out-of-plane strains, so EZZ and as well as XZ and YZ components, again, we can see that we match overall the the peak strains, along with some oscillations in the LVE model. We can also look at this for the maximum principal strain here on the top right, and the maximum axonal strain, so only in the white matter of the brain. And again, we see those same trends. One of the other things we can compare is just looking at that peak strain at 45 milliseconds at that magnitude. And here on the x-axis, I'm showing those strain components again, as well as the maximum principal strain and axonal strain. And I'm showing you percentile thresholds of the peak. So 75th and 95th percentile for the strain components, and then 50th and 95th for the maximum principal strain. And you can see in black, the experiment, in blue, the simulation, we match all the strain components, especially the in-plane strains, with a difference of about 0.005 strain, and then the maximum principal strain, it's about 0.01 difference. That's for the neck rotation condition. I did not show you the qualitative depictions of the neck extension, but we can also look at those peak strains in the same way. And you can see that if you compare the black to the blue bars here, we match the peak strains for all of the strain components, as well as MPS and axonal strain pretty reasonably here for the neck extension experiment. So here the takeaway is that we get similar magnitudes of peak strain from the models to the experiment in both loading conditions. The summary for this work is that subject-specific 3D brain models were created using a linear viscoelastic, or LVE, model derived from magnetic resonance elastography, and these brain material properties are derived from subject-specific data without further calibration. Even though we used some ex vivo data, we kept the magnitude and the shape of that original 30, 50, 70 hertz data the same. Under head rotation, the calibrated LVE properties were able to capture peak strains, but did not capture the brain dynamic response and showed poorer temporal agreement after peak strain. Under head extension, the calibrated LVE models were able to capture the peak strain and the dynamic response of the brain. For this work, I'd like to acknowledge my advisors here at Hopkins and the members of the Prince and Ramesh lab, as well as the brain biomechanics group that do a lot of acquisition of the MRI and MRE data I discussed today. This is under an NIH U01 project that includes Johns Hopkins, as well as Washington University St. Louis, University of Delaware, and the Henry Jackson Foundation. And I'll be happy to take any questions if you have them.